So what is a bond length? Now, bonds are generally assumed to be kind of like string. So because we have A which is bonded to B, and if I am assuming that there's a string connected to A and B bonds, the strings are what? It can like move, shrink, and it can what I can say, shrink hota hai aur ek kya hota hai? Stretch. So the because of temperature, you know, that the virtue of temperature, if the temperature is high, the atoms are going to move, and when the atoms are going to move in a bond, then bond is also going to stretch, right? तो ये क्या करेगा? स्ट्रेच भी होगा और थोड़ा श्रिंक भी करेगा, स्ट्रेच भी होगा और थोड़ा श्रिंक भी करेगा. So whatever the equilibrium distance is present, you know, between the centers of two nuclei of the bonded atom, that is known as the bond length. Because you can think about there are two extremes. एक बार अगर स्ट्रेच कर जाए बिकॉज ऑफ हाइट, बिकॉज ऑफ टेम्परेचर, और दूसरा एक्सट्रीम क्या होगा जब ये बिल्कुल श्रिंक कर जाए. So, like, what should we assume the bond length? Is this the bond length or is this the bond length? So, equilibrium distance we take generally. Okay, so that's how we define it, because bonds are assumed to be acting like a string. Actually, इसमें लिखिएगा पहला point. It is the equilibrium distance between the centers of two nuclei. Two nuclei of bonded atoms. Of bonded atoms in a molecule. Now, factors affecting bond length. Factors affecting bond length. Number one factor जो इसने affect करने वाला है, that is size of atoms. A part is size of atoms. So, for example, if I compare, so obviously, if the size of atom is larger, the bond length will also be larger. So you can say that bond length is directly proportional to size of atom. Right? Because if I have small atoms, they are going to have small bond length, because the distance between the nuclei of two atoms, this is the bond length. If I have larger bonds, sorry, if I have larger atoms, then obviously the distance between the nuclei will also be larger. The bond length will be directly proportional to the size of atom. That is why carbon-carbon bond is smallest, followed by silicon bond, followed by germanium bond, and so on. Second part is bond multiplicity. Bond multiplicity or bond order. Bond order is actually a concept of molecular orbital theory, but you can understand. For example, single bond is bond order 1. If the bond order is 2, that means there is a double bond. If bond order is 3, that means it is a triple bond. So if we have more bonds, there is more attraction between the nuclei. And if there is more attraction, the nuclei will be closer to each other. So bond length will be inversely proportional to the bond order. Will be inversely proportional to the bond order. Right? So you can say that carbon-carbon single bond will be the longest, followed by carbon double bond carbon, followed by carbon triple bond carbon. Similarly, nitrogen single bond nitrogen will be the longest, followed by nitrogen double bond nitrogen, and followed by nitrogen triple bond nitrogen, that will be smallest. Oxygen single bond oxygen will be largest, and oxygen double bond oxygen will be smallest. After this, we are going to write the bond angle. Now, what pen are we using? I think we are using a blue pen. Second one is bond angle. What is bond angle? Average angle between the molecules, between the average angle between the orbitals containing bonding electron pair, around central atom in a molecule. In a molecule. यहाँ देखिएगा, you have atom A, sir आपके पास atom B, and here also you are having atom B. Right? So this is, let's suppose theta angle. So this theta is known as the bond angle. So these are the orbitals which are containing the bonded electron pair. So theta is the bond angle. We have talked about bond angles in different hybridization also. So please write the next point: factors affecting bond angle. Now you can see that uh, when the steric number was 2, the bond angle was 180. Steric number 3, the bond angle went to 120. Then it went to 109.5 degrees, and so on. So you can see that if the steric number is increasing in this order, the bond angle is decreasing. So the first factor that we are going to take is steric number, or you can also see that it's dependent on the S character also. Okay, we will show all of those things. Right, the number one, A भी use कर रहे हैं क्या हम लोग? A भी, right? A steric number. Steric number. This is not really mentioned in the NCERT, so you can write or percentage S character. Percentage S character. You can see that steric number. Okay, I'm writing all the parts. Steric number, hybridization, and percentage S. Steric number जब 2 है, hybridization is SP, the percentage, and यहाँ पे bond angle भी है ना, bond angle. Percentage S is, we have two orbitals. This hybridized orbital जो है ना, the SP hybridized orbital, it is made by S and P. What is the contribution of S orbital? 50%. What is the contribution of P? 50%. The percentage S is 50%. Bond angle is 180 degrees. If the hybridization is P, sorry, if the steric number is P, hybridization becomes SP2. Now, how many atomic orbitals are taking part? There are 3 atomic orbitals taking part. What is the contribution of S? That is a 33%. 33% S character, and the bond angle becomes what? The bond angle becomes 120 degrees, no? 120 degrees, right? Now, when the state number is 4, the hybridization is SP3, then we have a 25% S character. And as you can see, what happens, the bond angle becomes 109.5 degrees. So from here, we can say that as steric number increases, bond angle decreases. Correct? Steric number increases, bond angle decreases. And also we can say as percentage S increases. देखिए, percentage S increase कर रहा है यहाँ पे, bond angle भी increase करे. Percentage S increases, bond angle also increases. So bond angle is directly proportional to the percentage S, and we can say bond angle is inversely proportional to the steric number. Now, if the percentage S character or the hybridization is same or the steric number is same, whatever you want to say, then it depends on the lone pair. The part lone pairs on central atom. Then देखिएगा. I'm talking about steric number 4. Steric number, it is equal to 4. We have different elements. For example, we have CH4, we have ammonia, NH3, we have water, that is H2. Now they have different numbers of sigma bond and the lone pairs, and they have different bond angles too. The sigma bond in CH4 is 4, the lone pair is 0, the bond angle is 109.5 degrees. In ammonia, we have 3 sigma bonds, and the lone pair is how much? The lone pair is 1. The bond angle becomes 107 degrees. When we have 2 sigma, 2 lone pair, this becomes 104.5 degrees. You can see that if a lone pair is increasing, the bond angle is decreasing. So you can say that bond angle, it is inversely proportional to lone pair on central atom. But this is only applicable when steric number is same. When the steric number is same, then only we have to look at the lone pair. If the steric number is different, then we are not going to look at the lone pair. Rather, we are going to look at steric number. Third is electronegativity. This is quite important. Key part is electronegativity. Now, I want all of you guys to please stop writing, and understand this electronegativity part. Till here, it was very much, we can say, like very easy logics we were putting, but right now you have to be a bit concentrated. Okay, please see here, guys. Electronegativity. Now, electronegativity, we have to look at two different things: electronegativity of central atom and the electronegativity of, यहाँ पे देखना पड़ेगा, ध्यान दीजिए जरा. If the electronegativity, if the you have to look at electronegativity when central atom is different, but surrounding atom is same. ठीक है, जो डिफरेंट हो रहा है उसी से डिफरेंस कुछ आएगा. अदर केस, दूसरा केस क्या हो सकता है? When the surrounding atom is different, but central atom is same. ठीक है. So whatever is different, you have to focus on that. So in this case, the bond angle, you will see that you will understand very easily. Bond angle, it is directly proportional to the electronegativity of surrounding. Sorry, central atom is the electronegativity of central atom. How? देखिए यहाँ पे. The example आपको बता रहे हैं. We have oxygen with 2 hydrogens, H2O, and we have sulfur with 2 hydrogen. This is H2S. Now, which is more electronegative? Because you can see now, central atom is different, surrounding atom is same in these two. If you are comparing between H2O and H2S, the surrounding atom is same, the central atom is different. Now, tell me, which is more electronegative, oxygen or sulfur? Which is more electronegative, guys? Which is more electronegative?
Oxygen.
Oxygen is more electronegative, right? Since oxygen is more electronegative, then what's going to happen? Oxygen is going to pull electron density towards itself. Now the shared pair of electrons are closer. When the shared pair of electrons are closer, what will happen? They will be repelling each other more. If they are going to repel each other more, then what's going to happen? The bond angle will increase. Make sense, Jasola? Please tell me.
Yes, sir.
Now, as bond pair electrons are closer in more electronegative elements, more electronegative central atoms, they will repel and bond angle increases. Another example we are going to see, when the surrounding atom is different, but the central atom is same. In this case, the bond angle, you will see that, is inversely proportional to the electronegativity of surrounding atom, surrounding atom different. In this case, we have to look at the example of ammonia, NH3 and NH3. So NH3, Now, whatever is different, you have to look at that. So, nitrogen is same. Nitrogen is not going to do any contribution in the bond angle. The bond angle's contribution will be with hydrogen and fluorine. यहाँ पे देखिए, hydrogen is more electronegative or fluorine which is more electronegative? Which is more electronegative? बोली गई, बोलो, which is more electronegative?
Fluorine.
Fluorine. Okay. See, I understand that some C2 batch people, they would not know what is electronegativity, but don't worry, you will understand it later on. Electronegativity is just the tendency to pull electron density towards a particular atom. So, right, in this case, the order आपको अगर याद करना चाहें तो हो सकता है फोन ClBr IsCPH, फोन ClBr IsCPH, ठीक है? You can remember this. ये हम लोग बात करेंगे इसके बारे में later on. So, in this case, fluorine is more electronegative. So, fluorine will be having electron density here. Away from what? Away from the central atom. And since the electrons are away from the central atom, then what's going to happen? They will be having lesser repulsion. If there is lesser repulsion, the bond angle will be less. है ना? If the electronegativity of central atom increases, bond angle decreases. Can you see that? Jasola, please tell me, guys.
Yes, sir.
ठीक है. So you'll take as bond pair electrons are far away in far away from central atom in less in more electronegative. ऐसे लिखना चाहिए ना, in compound with, in molecule with more electronegative surrounding atom. Therefore, they will repel less and bond angle will be less. Okay, Shama, just give me a second. Raise your hand once you're done. Waiting for Alina and Ali. Is everyone done? Yes or no, please tell me.
Yes.
Sorry. Let's check the bond strength or bond energy. Second, third part. So you write amount of energy required to break 1 mole of bonds of a particular kind between two atoms in gaseous state is called bond dissociation energy. तो जितनी ज्यादा एनर्जी लगेगी बॉन्ड तोड़ने में, तो if it is required to if it is required that a high energy is added in the system in order to break the bond. Breaking a bond, if it requires a high amount of energy, that means that bond was strong. If there is a bond which requires very less energy in order to break, that means that bond was weak. So bond strength, we can say that bond strength
So what is
is
written
directly
of
proportional. Sorry,
so
what's
what
that?
is written the particular?
Particular sign. Particular sign. We are going to learn about this bond dissociation energy in more detail in thermodynamics. And this is the definition that we have. But right now, I just want to give you an idea. We break bonds and then we talk about the bond strength. If we require a high amount of energy in order to break the bond, that means that bond was strong. If the breaking of bond required a less amount of energy, that means the bond was weak. Now, what are the factors that affect the bond dissociation energy? Factors affecting bond dissociation energy. First one is obviously the size of atom. So if the atoms are larger, they will be having longer bonds and it will be easier to break them. Because how a bond is made and how the bonds are strong or weak here, right? When we have smaller atoms now, so these smaller atoms, the nuclei of smaller atom which is positively charged, these are holding the electrons together. Here also we have positive charge, here also we have positive charge. In between we have the negative charge electron, negative charge. So these positive and negatives are attracting each other. Now, if they are closer to each other, that means the attraction will be very high. But if we similarly have a very large atom, and then if I have the bonded electrons, then you can see that this is the nucleus here, this is the nucleus here. And these are the valence shell electrons which are present. Now, how these valence shell electrons are together? Because this positive charge nucleus, this positive charge nucleus, and there is a negative electron. So it is attracted by these two, right? So there is attraction between these two. Now, if the nucleus is further away from the valence shell, then obviously it will be having lesser attraction. If the nucleus is closer to the valence, that means it depends on the size of the atom. If the atom is having a larger size, then obviously the valence shell electrons will be what? Further away. If the size is smaller, valence shell electrons will be closer. And if they are closer, they will be closer to the nucleus. And if they are closer, it will be difficult to break them because the attraction from nucleus and the electron will be very high. So we can say that bond dissociation energy is going to be inversely proportional to this sign. B part bond length. Here also, if the bond length is longer, it will be easier to break them. Because why will be the bond length larger? Because the nuclei of the elements are very far away. The nuclei are very far away. That means they will not be attracting the valence electrons as effectively. And if you are having a shorter bond length, then obviously the nucleus are closer together. Right. So bond length will be also what we can say. The bond dissociation energy is inversely proportional to bond length. C part, bond order, or bond multiplicity. If I have double bond, if I have single bond, that will be easier to break. If I have double bond, that will be difficult to break. From triple bond, that will be even more difficult to break. So you can say that bond dissociation energy, it is directly proportional to the bond order. And we can say that single bond is easiest to break, followed by double bond, and followed by triple bond. In this, we have one particular important exception that we have to study. Hopefully, you have written till here. Write a note. See, if I compare F2 and Cl2, right? If I compare F2 versus Cl2, fluorine versus chlorine. Now, fluorine versus chlorine, the expected order was obviously fluorine is smaller in size. That is why fluorine will be difficult to break, right? And it should have higher bond dissociation energy than that of fluorine. The bond strength of fluorine should be the fluorine bond should be more strong because it is smaller. But the actual order is fluorine is easy to break rather than fluorine. Now, what the reason is? See, fluorine atom is something like this. Fluorine, single bond fluorine, there is 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Fluorine atom is Cl and Cl. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, both the atoms they are having 3 lone pair electrons. But the difficulty with fluorine is that the fluorine is having 3 lone pair electrons and it has only second shell. There's a second period element, that is why it is only having 2 shells. And 2 shell means the maximum capacity of the 2 shell electron is 8. The second shell can hold how many electrons? It can hold 8 electrons. But the third shell can hold 18 electrons. How many electrons does the fluorine has right now? Only 8. So when the maximum capacity is 8 and we are filling 8, then at that case the repulsion will be very much high. The repulsion between the lone pair electrons will be so high. And because of the small size, what happens? There is a repulsion between the lone pairs of 2 different fluorine atoms. When the 2 different fluorine atoms they are going to repel each other, it will be easier to break the bond. Because internally itself they are having some kind of repulsion and they're going far away. So it will be easier to break them apart. What is the reason? Reason is extremely small size of chlorine causes repulsion between the lone pair, of combining atoms. Therefore, it is easier to break. Copy this down, raise your hand once you're done. Waiting for Ali and Sabiha. So till here we have all the valence bond theory and उसमें जितने भी चीजें थी. Now we are going to learn the last theory for bonding theory, that is the molecular orbital theory. Okay. So please write the heading. Molecular orbital theory. Now, I will put up a very simplified version of the molecular orbital theory. Okay. Although it is the most advanced theory that is present till now with respect to bonding theory. Like even obviously there are levels to molecular orbital theory. You will be learning a very surface level information about molecular orbital theory. If you are going to pursue chemistry later on, then you will be learning very much details of the molecular orbital theory. Right now in this class, we are only going to apply the molecular orbital theory in homodiatomic molecules such as H2, Cl2, F, not even Cl2, F2, O2, C2, V2, E2, these type of things. Only homodiatomic. And we are not even going to take the heterodiatomic molecules such as HCl. How the molecular orbital theory, what molecular orbital theory says about HCl. How can we apply the molecular orbital theory about HCl? We are not going to discuss those things. Now, what is molecular orbital theory? It's very simple. Initially, like the concept is very what we can say, very logical. See, we know that in atoms, electrons are in atomic orbit. In atomic orbital. So, in molecules, electrons are in molecular orbital. Electrons are in very simple idea. If you are saying that in atoms, electrons are in atomic orbitals, so obviously there will be orbitals because with the combination of atoms we get molecules. I know. And in atoms we have what? Electrons in the atomic orbitals. So in molecules will have certain different types of orbitals. We will have certain different type of orbitals, but even in molecules, the electron will be in orbitals. And what are those orbitals? Those will be molecular orbitals. Okay. So what are molecular orbitals? Simple. When atoms combine, they form molecule. When atomic orbitals will combine, they are going to form molecular orbitals. So next thing, this we are going to write as AO, atomic orbital, and we are going to write MO. We are going to use this word MO for molecular orbital. Right. So MO are formed. Our MO form. MO are formed by linear combination of AO. This linear combination of atomic orbital, this is in short known as LCAO. Linear combination of atomic orbital. अब इसको हम लोग को डिटेल में समझना पड़ेगा. We will have to understand what is LCAO in detail. Till here everything is fine. Yes or no? Please tell me, guys.
Yes, sir.
Linear combination of atomic orbitals. Linear combination of atomic orbitals. LCAO. Linear combination of atomic orbitals. ध्यान दीजिएगा जरा. Now, I want all of you to stop writing because you don't have to write anything. Okay. Basically, please don't write anything. You don't have to write these things. I'm just going to explain. After that, we are going to write. You have atomic orbital AO plus AO will give you M. Atomic orbital will give you M. But what is atomic orbital really? Atomic orbital is this. Atomic orbital is this. Atomic orbitals are this and this. These are going to combine. But if you remember, in atomic structure, we have studied that atomic orbitals are really what? Psi, wave function. Psi is the wave function that represents electron present in an atomic orbital. And when we do the psi square, we get the probability density, and from that probability density, we have got these shapes. That okay, fine. If I talk about the s orbital, then the s orbital is very closer to the nucleus. The probability of finding the electron is just very closer to the nucleus. And as we go away from the nucleus, the probability of finding electron it slowly decreases. Now, this type of shape we have got from what? From the psi square, which is a mathematical wave function. Now, if I talk about waves, and you must have seen this sign in the atomic orbitals if you have seen the notebook, or if you have seen the textbook, plus, minus, minus, plus, like this. You've also seen this in this same chapter, balance point theory. Now, what are these plus and negative signs? Because whenever there is a wave, it will have a phase. There will be a positive phase, there will be negative phase. So when we write some atomic orbitals like this, plus and minus, this represents the positive phase, this represents the negative phase, right? Now, please see. If there are atomic orbitals which are combining in this order, right? So they are combining in this manner. That means when you are going to combine them, if you are going to overlap, if you are going to interference, this is known as wave interference. When two waves are going to interfere, if there is what we say constructive interference. If there is a constructive interference, that means positive is meeting positive, negative is meeting negative, then please see what is going to happen. Very important. Don't write this now. This part will meet with this part will meet with this part will meet. and this top part will meet with top part, this zero part will meet with zero part, this end part will meet with end part, negative is meeting with negative, positive is meeting with positive, then obviously there will be a bigger wave form. Does this make sense? Yes or no? Please tell me.
Yes, sir.
Now, if we have
Yes,
a
sir.
opposite scenario, when we have waves which are plus and minus, and here I have a opposite wave. We have minus and plus. Now, if I am saying that this is plus 2 and this is minus 2, you can see that when we are going to add these two types of waves, then what is going to happen? Plus 2 and minus 2, they are going to cancel each other out, and we call this type of wave as, with this type of interference or combination, as destructive interference. And you will not get anything in the, as a resultant of, if you have constructive interference, you are getting double. Whatever we had, you are going to get double. But if we had destructive interference, then we are not going to get any waves here. Your better are going to cancel each other out. Now, let me also tell you guys about the, there are two types of combination that can take place. If you have sine, so by the way, you can have sine. Suppose we have two atomic orbitals, A atomic orbital and B atomic orbital, right? So psi A is combining with psi B, and both of them are having the same thing. Both of them are having the same sign. Or another way could be, देखिए ना आपके पास, if I am talking about atomic orbitals, then 50% of atomic orbitals if I take for positive, then 50% will be negative just by symmetry. Similarly, in the B also 50% will be positive and 50% will be negative. So you can have positive positive interaction, negative negative interaction, positive negative interaction, and negative positive interaction. So half of the interaction will be constructive because positive positive interaction is constructive, negative negative interaction is constructive, positive negative and negative positive are destructive. So two interactions are constructive, two interactions are destructive. Fine. So in that case, there is only two possibilities: 50% constructive, 50% destructive. Now please listen. You can have one condition if you are having psi A plus psi B same sign, or you can have psi A plus psi A is in positive sign, and we are having constructive only plus minus psi B. The phase of B is opposite to that of A. I'm not saying that B is negative only. If A is positive, B is negative. If A is negative, B is going to be positive. So these are the two types of interference that we can have. Now, if I want to talk about the probability density, now this is, if I want to talk about the probability density, I have to take the square. Now, what happens when we square it? Psi A square plus psi B square plus 2 psi A psi B. Now, in this case, psi A square plus psi B square minus 2 psi A psi B. Here we are having a 2 psi A psi B that is positive. Here we are having minus 2 psi A psi B. This plus 2 psi A psi B, it is responsible for, this is responsible for the increase in electron density between nuclei. And this is responsible for decrease in electron density between nuclei. And as a resultant, when there is, if you are having one nucleus and another nucleus and there is electron density between them, इसी को तो bond कहते हैं, there is electron density between them. So A and B atoms, they are having in between, there is a bond. And this type of molecular orbital that is formed by the constructive interference that is known as bonding molecular orbital. So 50% will be bonding molecular orbital. And if you don't have any electron density between A and B, so the nucleus, positive nucleus, they are going to be what? There is no electron density here. So there is no bond. So this is known as anti-bonding molecular orbital. So we get 50% bonding molecular orbital and we get 50% anti-bonding molecular orbital whenever there are two atomic orbitals combining, we will get two molecular orbitals. One will be bonding, the other will be anti-bonding, just by the sheer probability that half of the psi is going to be same and half of the sides are going to be opposite with the opposite phases. Right? Now, अब यहाँ पे आपके पास कुछ चीजें हैं। ऑब्वियसली यहाँ पे देखिए कि इफ देयर इज, यहाँ पे देखिए इफ देयर इज पॉजिटिव चार्ज हियर एंड दिस इज इलेक्ट्रॉन टू नेगेटिव, so obviously there will be positive negative attraction. But in this case, this is positive, there is no electron density between them. So obviously there will be what? There will be repulsion. So whenever there is attraction, this will be having lower energy, will be having lower energy, and this will be having higher energy. This will be having higher energy. Right? We are going to look at the shapes and everything slowly. Now you write. All of you understood this a bit? Yes or no? Please tell me. I understand that this is going to be a bit difficult. You are learning the most advanced theory in chemistry about bonding. Chemistry is nothing but about the bond formation of bonds and the breaking of bonds, and you are learning the most advanced theory. It is going to be a bit difficult to understand, but hopefully, if you revise these things, you will be able to keep it in your memory. Yes or no? Please tell me.
Yes, sir.
Make sense till here? Fine. Now, I understand that obviously these things must not have been covered in the school, neither it is present in the NCERT, but obviously now either I will have to make you understand slowly and slowly that I have tried to do, or I would just give you things and you have to memorize them. Right? Right. I hope you understood that the formation of bonding molecular orbital and anti-bonding molecular orbital, the important concept is that 50% is going to be combining in same phase, 50% with what? 50% in opposite phase, just by the sheer probability, only because of probability. Because whenever there are bonding taking place, there will be millions and millions and millions and millions, 6 times, 7 times, 8 times millions of atoms if I take one mole. So on an average, there will be 50% bonding and 50% anti-bonding. चलिए इसके बाद आप लोग लिखिएगा formation of MOs, that is molecular orbitals. We're having LCEO. In LCEO, first of all, we are going to look at formation of molecular orbitals. Formation of molecular orbitals. Number one, molecular orbitals are formed by combination of, please write this with me and write it quickly, of atomic orbitals of same or slightly different energy. Are formed by combination of atomic orbitals of same or slightly different energy of two different atoms. है ना? Hybridization से confuse मत होइएगा. In hybridization, we have the combination of atomic orbitals and the mixing of atomic orbitals of the same atom. Here we need a different atom. One atom hydrogen, the other atom another hydrogen. Carbon, then two different carbon atoms. Two carbon atoms are going to form. Next. Next is what is the question. Half of the MO formed are by combination of atomic orbitals with same sign. They give rise to bonding molecular orbitals. That is BMO with lower energy. Second, half of BMO form are by combination of atomic orbitals with different sign of psi. They give rise to anti-bonding molecular orbital ABM with higher energy. With higher energy. तो, चलो ठीक है, यहाँ पे तीसरा पॉइंट लीजिए।
सर आपने 2 बार सेकंड पॉइंट लिखा है।
नहीं, 2 बार नहीं लिखा है हमने, बीएमओ इधर एबीएमओ। ठीक है, देखिए साई ए प्लस साई बी will give rise to psi AB, ठीक है, which is will be known as BMO. And when you have psi A plus with opposite sign psi B, which will give rise to psi star AB. Fine, तो psi star AB को क्या बोलेंगे हम लोग? ABMO. Fourth point. Now we are going to denote BMO as psi and ABMO as psi star. Number of MO forms is equal to number of atomic orbitals combining. Copy this down. Waiting for Ali, Shaima, and Zainab. Waiting for Zainab. Let's take the shapes of C. First thing that we have discussed is formation of MNO. Then next thing that we have to discuss is shapes of molecular organisms. So right now we are having 1s and 1s. The first one, when there is 1s and 1s are combining with each other. Okay, the combination of 1s orbital with another 1s orbital, then it is going to give you what? 1s and 1s. Fine. So when they are going to combine with each other, then they will give rise to what? Two atomic orbitals. Sorry, this is AO's atomic orbitals. It will give rise to two bonding orbitals, two molecular orbitals. The lower in energy will be bonding molecular orbital, and how it will look? It will look something like this. when the electron density is going to completely mix, it will be looking like something like this. ऐसा लिखेगा, right? Now the nucleus are here. देखिएगा, atomic orbitals. This will be nucleus and this will be nucleus. The nucleus are here. You can see that electron density is between large electron density is between the nuclei. Because of large electron density between the nuclei, this nucleus is attracted this side. This nucleus is attracted this side, and there is a bond formed. Obviously, this is what? This is 1s, and because the electrons, we can see that the combination is taking place on the internuclear axis. That is why it will lead to the formation of a sigma bond. This sigma bond is formed by 1s. We will call this sigma 1s. Okay, so here what's happening? There is attraction in this case, and because there is attraction, there will be stability. This is stable, and this will be having lower energy. And you have to just sign hoga na, if I talk about the sign of this wave, like molecular orbital is also going to have sign, so this will be completely positive or completely negative, है ना? Like both the sign will be same, either completely positive or it will be completely negative. Okay, you can write it like this, positive and positive. Now, when we are going to have the destructive, then it will look something like this. Hmm. So, see, the two atomic orbitals, they combine with each other, and because of destruction, like whatever combination took place, utna electron density khatam ho gaya, right? So here is the nucleus. There are two nuclei, and in between there is no electron. Destruction, whatever combined, wahan pe destruction ho gaya. And how will the destruction take place? Only if they are having opposite signs, so plus and minus. If you look at NCERT, it is given something like this. Like काजू शेप का कुछ तो बनाया हुआ है. I just made it. So obviously here you will find a node. Between the nucleus, there is no electron density. That is why this will be positive. The nucleus is positively charged, है ना? This means the plus and minus are sign of phase. Wave का sign है, charge नहीं है ये, ठीक है? ध्यान रखिएगा. This is wave. Now the nucleus are positively charged. They will be repelling each other. In this case, what will be happening? Repulsion. That is why unstable. Because of unstable, it will be having higher energy. और भी चीजें आती हैं, वो सारी चीज लेकिन आपको पढ़नी नहीं है. फॉर एग्जाम्पल इसमें सिमेट्रिकल होता है, अनसिमेट्रिकल होता है, वो सारी चीजें. Copy this down, raise your hand once you're done. Okay, इसका नाम क्या होगा? By the way, this will be known as sigma star 1s. Sigma star because it is anti-bonding, and because 1s because it is made by the 1s atomic orbital. This is BMO. This is ABMO. अरे अच्छे से रिवाइज कर लीजिएगा इसको. Just waiting for Justine. Justine, raise your hand if you're done. Justine, Justine, are you still writing? ठीक है, so in 1s you can see that we have only formed sigma bond because the atomic orbitals were combining on the internuclear axis. याद है आप लोग? Do you remember internuclear axis? Nobody remembers internuclear axis. 2p mixing. In 2p mixing, case 1 will be. Guys, nobody remembers internuclear. Internuclear axis. Tell me. बोलो. Oh my god. See, yes or no? Saima remembers. So case 1 is orbitals combine on internuclear axis. Generally, this internuclear axis is taken as the Z axis. In NCERT, they have taken this as it's been taken up. X ले सकते हैं, Y कुछ भी ले सकते हैं. This is taken as Z axis. This is not one p orbital, rather one lobe of p orbital. Just rotate it. This is one p orbital. This is another p orbital, and they are meeting like this on the axis. जहाँ पे जो overlapping जो हो रही है, and the nucleus, they are on the same axis. This is the nucleus, this is the nucleus, and here only there is overlapping happening, right? So overlapping is happening in the internuclear axis, the axis which contains the two nucleus. There only we are having the combination or overlapping. Next, here this is also going to give you two different molecular orbitals. One molecular orbital, it will look something like this. Like whatever lobes they are combining, they will combine with the same sign, and they will become something like this, very large lobe in between. Right? And the lobes which we are not combining, they will become smaller in comparison. तो छोटे नहीं हो जाते, in comparison they become smaller. In comparison they become smaller. So if the combining lobes were having positive phases, this will be having negative phases. Okay? Now this is what sigma, because the overlapping is happening on the internuclear axis. We'll call this sigma 2p, and sigma 2p is Z, because obviously if the internuclear axis is Z axis, this axis is Z axis. So these orbitals will also be what? This will be PZ orbital. Now here also we are writing this is going to be BMO, lower energy. Now what will happen to the APMO? The combining lobes, they will become smaller. The combining lobes, they will become smaller because वहाँ पे destruction हो गया. ठीक है? So these lobes have become smaller, and the other lobes will be comparatively larger. Like this. Now, where is the nucleus? The nucleus is here. The nucleus is here. So we have just shown this, but this is going to be very small. Obviously, this will be having negative and this will be having positive sign. That's why there has been destructive interference. This is negative, so this will be positive, and this will be positive, so this is negative. So this is going to be known as sigma star 2pz. And this will be the anti-bonding molecular orbital. It will be having higher energy. Waiting for Abir, Jasleen, and Shaima. Just waiting for Jasleen. Just waiting for Jasleen. Oh my god, बहुत टाइम लगाते जसलीन आप तो. Jasleen, raise your hand if you're done. Done. Right, case 2. Atomic orbital combined above and below internuclear axis, that is the Z axis. So right now our orbitals are not going to be on, our lobes are not going to be on the Z axis. So it will look something like this. We can find this. Give me a second. See it. So the atomic orbitals are combining like this. Okay? Atomic orbitals are combining like this. Now, this is the internuclear axis. And you can see that on the internuclear axis, there is no combination. There is combination above and there is combination below. Now, obviously, if the internuclear axis is the Z axis, these atomic orbitals will be either 2px or this will be 2py. Because it cannot be the Z axis. Because if it was the 2pz, then three lobes will be on the axis. Because this is what? This is the Z axis. ये आपके पास क्या Z axis? And this will also give rise to two different molecular orbitals. When these two lobes are combining with each other, we have seen the shape that atomic orbital will, sorry, the molecular orbital will look something like this, above the and below. Above and below the internuclear axis. ठीक है, ये internuclear axis नीचे. So if the above was having positive phase, the below will be having negative phase. Right? These two lobes will be having positive, positive, negative, negative, then they are overlapping. Now this is going to give you a phi orbital. It will be phi 2px or phi 2py. And obviously this is going to be what? Bonding molecular orbital. Bonding molecular orbital, that is lower in energy. And this part here, ये थोड़ा सा बनाना difficult होता है. These two are not going to combine, these two are also not going to combine, so it will have something like this. If I can rotate it, it will be better. Let me wait a second. Try it once again. Hopefully this will be fine. No. This would work. See. So here we had a nucleus. This was a nucleus, and this was a nucleus. In between, there was destructive interference. So obviously, this will be having a positive sign. This lobe will be having positive. This will be negative. So they combine and they and destructive. So complete electron density is gone. Here it will be negative and this will be positive. Now this will be known as phi star 2px or phi star 2py. And obviously, this is going to be anti-bonding molecular orbital, which will be having higher energy. All of you done? Thank you. Next, we have, please write, conditions for LCA. These are shapes, formation of MO. Now, please write conditions of LCA. Conditions for linear combination of atomic orbitals. LCA. We have seen one condition. atomic orbital should have same or slightly different energy. Atomic orbitals should have same symmetry. है ना? ऐसा नहीं कि 1s वाला like s orbitals cannot combine with p. P will combine, s and s will combine because s orbital is completely symmetrical, completely positive phase. But if you look at p orbital, this may be positive and negative phase. So positive and negative phase will have this is not the symmetry of this p orbital is not same as that the symmetry of the s orbital. That's why they are not going to combine. Atomic orbitals should have maximum extent of overlapping. That means a very large atomic orbital cannot combine with very small atomic orbital. The extent of overlapping should be maximum. That means atomic orbitals of the same principal quantum number, like 1s and 1s will combine, 2s and 2s will combine, 2p and 2p will combine, 4s and 3d can combine. बाद में वो सब आपको देखना तो नहीं, 4s and 3d will combine. Now we are going to have a detailed look on the energies of different molecular orbitals, because as in atomic orbitals we use off-bound principle in order to fill the electrons. Here also we are going to use the off-bound principle only. So the molecular orbitals having lower energy will be filled first, and the molecular orbital having higher energy will be filled later on. Energy of orbitals is going to be a complete topic, but right now थोड़ा सा आइडिया लगता है आप लोगों को energy of molecular orbitals. Now, if I look at the different types of bond that they have made, or if I look at the different types of what we can say atomic orbitals that we are using. So the atomic orbitals that we are using is 1s, which is having lowest energy. Then we have 2s, which is having next energy, and then we are having 2p. So these are the only orbitals, atomic orbitals that we are using. So from 1s, we are going to get sigma star 1s, which will be having higher energy. We will get sigma 1s, which will be having lower energy. First, you will have sigma 1s, then we will be having sigma 1s star. Now, in 2s, we will be having sigma star 2s, and we'll be having sigma 2s. Now, the energy of these orbitals will be lesser than the energy of these orbitals. Why? Because the principal quantum number यहाँ पे 1 है, यहाँ पे 2 है. So obviously this is in a larger shell. The energy level of 2s is already greater. So the sigma 2s or sigma star 2s, all of these will be what? Greater than sigma 1s or even sigma 1s star, which is not anti-bonding. Even though this is anti-bonding and this is bonding molecular orbital, these anti-bonding sigma star 1s will be lower in energy than sigma 2s. Why? Because of what? Because of the higher energy level of the second shell. The principal quantum number is 2. So this is further away from the nucleus. That is, it will be having higher energy than even the sigma star 1. Now, in 2p, we are having two different types. We are having sigma star 2pz, and we are having sigma 2pz. Okay, and we are also having what? After this, we will be having the pi star 2px, that will be equal to the pi star 2py. Both of these will be having equivalent energy. And pi 2px, the bonding one, they will be also having similar. Pi 2px and will be equal to pi 2py. ठीक है, this is to confirm. इसके बारे में we are going to have a look on it. ठीक है, this is going to change. But overall, you can say that 1s, the molecular orbitals formed by 1s will be having lower energy, that is formed by 2s, and that will be lower energy that is formed by 2p also. In this, you are going to have some talk later on, but for sure, the atomic orbitals that are formed by 1s, the molecular orbitals that are formed by 1s will be having lowest energy, then 2s, then 2p. Copy this down.